I'm Dr. Tom Killian, an atomic physicist in the Department of Physics and Astronomy at Rice University. In my laboratory, I have several experiments studying the behavior of atoms and plasmas at super cold temperatures, just a fraction of a degree above absolute zero. When atoms and ions are this cold, they move incredibly slowly, as if they're moving through molasses. And they behave very differently than systems at normal temperature. We can make gases in which the quantum mechanics dominates the interactions. And we can make plasmas that are so cold that they freeze into liquid or solid states that mimic the behavior of the interior of Jupiter or the surface of a neutron star. Here is one of the experiments. We use all these lasers to make our ultra-cold atoms. The element we use is strontium, which interacts very strongly with blue light. The light actually pushes on the atoms, and we use lots of tricks to make sure the light is always slowing the atoms down, which makes them colder. If you look into the vacuum chamber, you'll see about 400 million strontium atoms. And the light that you're seeing is actually the light from the lasers that is cooling them. They blink on and off about every second, because about every second we trap a new cloud of atoms, and then we do an experiment that blows them away, and then we retrap another cloud of atoms. In this case, we're shining a very, very bright laser onto the atoms that knocks an electron off of each one, which turns our atoms into a plasma. But because we start with ultra-cold atoms, the plasma that we make is super, super cold. The coldest plasma that's ever been made in the universe.
My name is Natalie Martinez Escobar, and I work in Dr. Thomas Killian's lab. And I am involved with his ultra-cold neutral atoms experiments.
Usually on a daily basis, I'm trying to build lasers and get them to work in such a way that we can control exactly what wavelength comes out, and the beam shape looks good, and we can use them to actually make atoms change atomic states and all that kind of stuff. So I'm just trying to get all of these lasers to work really predictably and well in the way that I want them to. This laser I built myself. It's inside a vacuum chamber because we want to cool it down to liquid nitrogen temperature so that we can get the laser to a different wavelength of light than we would normally have it. So it's actually not a laser that's commercially available, which is why we had to do this to it. So it's pretty interesting.